Okay, the next course that you had taken is the calculus, and you have learned that there are there are two branches of calculus, namely the differential calculus, right? And this is different from the course that we have right now, the differential equations. That's different. Okay, so differential calculus and the integral calculus. Okay, and note that whenever there's a new branch of mathematics that's being discovered or developed, that just simply means because there are a class of problems that that can't be solved by the previous mathematics. Okay, so for this, the calculus was actually developed uh, because the the problem during that time around 17th century or 16th century, the previous mathematics like the algebra, geometry, and trigonometry, they were not able to solve certain problems. Okay, so that certain problems is all about the tangents of a curve. Okay, tangents of curves or areas, right? Total areas bounded by a curve. Total area bounded by a curve. Okay, and what else? Let's say the maximum values or the minimum values. Okay, and um, many more. Okay, so what this means is that it can be described that the problems that they were trying to solve is on, let's say, more in geometry and also the physical situations. Okay, so this one, the tangents and the areas there, they're about geometry, and maximum and minimum values, or also the rate of change, or let's say instantaneous velocities, right? So this is this is a physical problem that we're not solve or that can be solved using the previous mathematics. Okay, so to discuss detail, what this means is that, for example, I have a graph like this, and let's say this is my independent variable, and this one is my dependent variable. Now, and let's say I have a curve um, that's a line. Okay, so if that's a line, then if I ask you what is my slope, or what is the line that is tangent to this curve, right? Let's say this tangent line is actually the same. It's actually that, or this tangent line coincides with this curve or our functions. Okay, so that means that uh, if we want to find the tangents or the slope, that just simply means that the delta y all over delta x, right? So this is constant all throughout. So if I ask you to find the slope right here at this point, then you can actually solve that. And if I ask you to find the slope at this point, then it's just the same thing, right? So this in this type of problems, you don't actually need the calculus to be able to solve the slopes of the tangent lines. Okay, but the problem is, what if instead of having a straight line, instead of having a straight line, what if my curve is something like this, right? So I have a nonlinear curve, and if I am asked to find what's going to be the slope here, right, or what's going to be the slope right here, so that's going to be different all throughout the the curve. Okay, so in this case, that's going to be, okay, what you need is actually, if you want to zoom this, so for example, this is my infinitesimal segment of the curve, right? Okay, so what that means is I have to take a small value right here, right? The smallest difference. I have to take the smallest difference, right? And so this is my delta x and delta y, right? So it's something like I'm going to have this delta x approaching zero, because if I have this delta x right here, I have this large delta x. That's the average values, and I can't actually obtain the exact the exact um, the exact slope at the specific point. So if I shrink this delta x to zero, right? So if I shrink this to zero, right? So that means that I can approximate the value of the slope, right? So that's why the expression for this mathematics is right, is limit as delta x approaches zero, or right, let's just write here the slope is limit as delta x approaches zero of delta y all over delta x, and that brings out the concept of the derivative, so which is dy all over dx. Okay, and the same is also the problem for areas. Okay, so if this one is related to the very small value, the area is something like it's related to the bigger value. Okay, so what if I have this function right here, and what if what I want to find I want to find the area bounded by this. Let's say from point A to point B. Okay, so if I'm going to find the area, okay, so this is just simple. Why? Because this is simply a regular shape. So in that case, I don't need the calculus to solve this. But the problem arises if I have a curve that's nonlinear, right? For example, something like this. Okay, so if that's the case, then what if I am asked to find this area, right, from point A to point B? Okay, so if that's the case, then that's actually we will need the calculus to be able to solve this problem. Okay, and the concept is also to assume an infinitesimal segment, right? So something like the delta x is approaching zero, and this distance right here, that's our function f of x, right? So that's why it was written that area is equal to, or maybe right here, area is equal to integral of f of x dx, right, from point A to point B. So that's what you studied in the calculus, and the main theorem in this calculus subject is that this differential calculus and this integral calculus, they are something like an opposite to each other. Okay, so if this is about the slope, this is about the area. So this is about the smallest thing. This is about the biggest um, the biggest thing, right? And also, although we only discuss in terms of geometry, just take note that this is also uh, this is also a description that can, or this can also be related to the physical phenomena, like for example the maximum and the minimum values. Okay, and also the rate of change and instantaneous velocities and things like that. Okay, so enough of these previous math courses, and now we'll be moving on to our course. Okay, what is this differential equations? Okay, so after you have taken the calculus, the integral, the differential, and also the basic math courses, um, we this is now the the course, right? This is now our course, uh, and what what this course is all about is from the word itself, differential equations, meaning that equations, okay, so that involves equations that involves derivatives. Okay, so basically, differential equations is, of course, that's all about um, the equations, or solving equations, right? Solving equations involving derivatives. So let's write it here: solving equations that involves derivatives. Okay, so why do we need why do we need to have a separate subject on this differential equations? Why can't we just solve using the all right using the differential calculus, right? Because after all, this differential calculus and integral calculus also involves um, involves derivatives already. Okay, so the reason is that there are a lot of forms or types, right? Or types of equations that that involves derivatives. Okay, so because there are a lot of forms and types of equations that involves derivatives, then that simply means that um, there's no there's no one size fits all. All right, one size fits all. Okay, so take note of this phrase, one size fits all. Okay, so that means that there's no one solution that can solve all the differential equations. Okay, so meaning that there are a lot of methods, and some methods uh, are 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 easier for a particular type of differential equations, and other could be much difficult, or the mathematical operations are complex, or things like that. Okay, so that's why we need to study, right? So that's why we need to study the different methods, the different methods. Okay, so that's why I describe this course, these differential equations, as methods. It's all about methods of solving the differential equations, right? Or equations that involves derivatives. So it's all about methods. So there are methods for ordinary differential equations, or for first order differential equations, higher order linear, blah blah, and many more. Okay, so that is the the basic concept. Okay, so now I would like to get into the details um, of what's in our lecture handouts, that um, and also in the context of engineering, what we want is not just the equations, but rather the physical description, or the meaning behind the equations. That's what we want. Okay, so where do we encounter these differential equations? Okay, so for example, we have a free falling body, and we have this Tower of Pisa, right? And we have this body right here, and it's going to free fall, right? So it's going to free fall, and what if we want to describe? What if we want to to describe the position, right? The position along the y, right? So this is y, this is x. So we want to describe the position versus, or position as a function of, okay, as a function of time. Okay, position along the y as a function of time. Now for free fall, it's already been established that the the position is just simply or the rate of change of position. Actually, it's the second derivative. D squared y over dt squared is equal to a constant. So meaning that the acceleration, right? The acceleration. Okay, so how fast is it changing its velocity? That's the acceleration. Is a constant, and that constant is the gravitational constant. Okay, so this equation, although it's just basic, it is a differential equations. So how do you solve this? Then probably the basic calculus can can solve this. But for other types of equations, like for example, let's try another one. Okay, so let's try what if a falling body, except that this one, there's a parachute, right? Okay, and what we want is to model, or what we want is a mathematical description that describes the velocity, right? The position. Again, it's or let's say the velocity. I think it's better. The the velocity as a function of time, right? So what if we want velocity as a function of time? Okay, so how do we model this? Then of course, when doing mathematical modeling, then also we need scientific principles or governing laws and principles. Like for example, if we isolate this, let's say this is our system, right? And we apply the summation forces, let's say along y, because this is purely vertical direction. Of course, in reality, it could change along the x, right? It it uh it can change along the x. However, let's just assume for now it's gonna be a purely vertical direction. Okay, all right. So this is the equation: summation of forces y is equal to mass times the acceleration along the y. Okay, so what are the forces that acts on this system? Okay, so first we have the weight, right? We have the weight. So this is our weight, and then we also have forces that retards the motion, which is the drag force. Okay, so the weight is just simply the mass times gravity, and also the drag force is this is taken experimentally, and they say that the drag force is can be described using the equation b times v, um, uh, meaning that the drag force is a function of velocity or the square of the velocity. Now for some problems, it is assumed that it's linear, or, or let's just write b times, instead of square it's just linear, so bv, right? So let's take this. So therefore the forces, so we have, let's assume that the downward is positive. So if that's the case, then we can write the equation as the weight, right? So weight, okay, weight minus the drag force is equal to mass times acceleration along the y, which is just simply the gravity, right? Or let's just write a sub y. Okay, so therefore, um, if we substitute the values, this is just mg minus bv squared, right? It's equal to m. What is a? Now, acceleration is the rate of change of velocity with respect to time, so it can be written as dv all over dt. Okay, so in this equation, you will see that uh, our independent variable, right? Our independent variable is time, and our velocity is, or this velocity is our dependent, right? Dependent variable. This is independent. Okay, so we have the velocity variable right here in this derivative, and we also have another velocity variable in this term right here. Okay, so if we want to find the expression, let's say expression or mathematical expression or solution, mathematical solution. And when we say solution, we are referring to an equation that describes the uh, or that that describes the velocity as a function of time. So how do we solve this? How do we convert this to something like velocity as a function? All right, so velocity as a function of time. So how do we convert this equation, these differential equations, to this? So that's by the use of that's by the use of the methods that we will learn here in the differential equation course. Okay, and if you might ask, by the way, that then if this is the dependent variable, then this is the independent variable, then what is this m? What is this m? What is this g right here? So some terms are constants, right? We refer that as constants, or sometimes we refer it as parameters. So meaning, if this is just our variables, the velocity and time, and um, we set this value, for example, I mean a fixed value, or something like a constant, right? Then we can solve, or we can arrive, or we can derive the expression that velocity as a function of time. All right, there are still many more applications or physical situations wherein we can do mathematical modeling or express those situations or physical principles in terms of mathematical expressions. Okay, anyway, as we go through along these subjects, we will also do um, applications, physical problems. Okay, so going back again, when we say differential equations, I mean the course on differential equations is all about methods, right? Finding, uh, methods of finding, uh, methods of finding the solutions for equations involving derivatives, equations involving derivatives. Okay, so it's all about methods. Okay, so um, there are it's simply because there is no one size that fits all, and these methods is simply because there are many types of many classes of differential equations, like for example first order, higher orders of partial differential equations, and within that first order, let's write it here. So we have first order differential equations. We also have higher order, meaning order greater than 1. Okay, and we also have partial differential equations. And within this class, there's still many subclass. Like for example, separable equations. So these are equations, or these are differential equations wherein it can be solved by just separating the independent variable and the dependent variable. And also there are equations like exact equations, linear equations, and things like that. Linear equations, and right here we have homogeneous equations. And by the way, these homogeneous equations is different from the equations, another subclass of equations that has homogeneous coefficients. So that's different from this one, homogeneous equations. And there's also a non-homogeneous, right? And there's a lot of techniques. Okay, so the main point again, it's all about techniques, various techniques or methods, so that we can arrive into solutions. And when we say solutions, sometimes what we want is the mathematical expression, not the value itself. Although we can also obtain the value by, let's say, if we input some boundary conditions or initial conditions, we can obtain the exact values. But sometimes what we just want is just simply the mathematical expressions. Okay, so that's what we mean when we say solutions. All right, so I guess that's all that I can say, and I wish you an enjoyable experience throughout this course. Okay, so that's all.